to everyone. It's my pleasure to introduce Professor Sudharman Jayaweera, a good friend and an expert in fundamental research related to physical layer, things like wireless and digital communication, statistical signal processing, detection and estimation, information theory, machine learning and AI, and game theory. These are his forte, with decades of experience in fundamental research and related to communications. Also, practical experience. He has participated in several industry-related efforts. And at this point, he is a program manager at National Science Foundation. It is a pleasure and honor to introduce Sudharman Jayaweera, Professor Sudharman Jayaweera, to give this presentation as part of the webinar series on advanced air mobility. So thank you, Dr. Jayaweera. Please proceed. We take about for all the audience, please mention your questions in the chat, and if possible, if you can wait till the end of the seminar, then I will facilitate a question answer session. But if it is important and you want quick answer, you can also mention that in the chat. Thank you, and enjoy the presentation. Please proceed, Dr. Jayaweera.
All right, thank you. So I hope that you guys can see me and see my slides. Okay, thank you, Kamesh. Thank you for that nice introduction. Let's get started. So this is part of the IEEE Vehicle Technology Society webinar series on advanced air mobility. Thank you for IEEE VTS for their sponsorship. So what we're going to talk today about 3D beamforming for unmanned aerial vehicle-based communications. Okay, so let's just start with the little bit about the Gs. So the going from 4G to current 5G wireless networks, there were performance expectations. In particular, the 5G identified three usage cases: the enhanced mobile broadband, the massive machine-type communications, and the ultra-reliable and low-latency mobile communications. In many cases, the performance indicators, performance metrics related to those in 5G were supposed to be 10 times better compared to 4G. For example, the peak data rates was supposed to be going from 1 gigabits per second in 4G to about 20 gigabits per second in 5G. And the same way, the latency, which was about 10 milliseconds in 4G, was supposed to go from 10 milliseconds down to about 1 millisecond. Currently, the 5G is under deployment in many places around the world, but we already have been moving forward with the next generation wireless. Now, the 5G expected to achieve those performance improvements using a combination of various new and improved technologies. For example, to enhance the data rates, in many cases, the massive MIMO was seen as an important ingredient. And also, in terms of the network architectures, using the ultra-dense small cells, as well as heterogeneous nets or the head nets. And the scalable OFDM numerologies that allows using different size or different subcarrier widths was another approach. Along with the massive MIMO, one of the most important techniques that was under consideration for 5G is millimeter wave communication. And the millimeter wave communication is supposed to address the issue of limited bandwidth in traditional sub-6 gigahertz regime and open up much higher bandwidths for the 5G communications. But along with the millimeter wave communication, an important technique is the 3D beamforming. Compared to the traditional two-dimensional beamforming that I will talk in a minute, the 3D beamforming allows one to consider beamforming in also vertical or the elevation dimension. And sometimes because of that, it's called the full dimension MIMO or 3D beamforming. Now, as I mentioned, with already 5G under deployment, the ITU INT, which is responsible for the 3GPP specifications, already have started the next generation, the standardization, which is 6G or IMT 2030. Now, the IMT 2030 introduced 6 usage scenarios compared to the earlier 3 usage scenarios that was considered in 5G, the enhanced mobile broadband, the massive machine type communication, and the URLLC or the ultra reliable low latency communication. In 6G, these are given new names. The enhanced mobile broadband has changed the name to immersive communications to cover all the immersive applications, AR, XR, holographic communication, things like that. And the massive machine type communication is simply called the massive communication. And the ultra reliable low latency communication has changed the name to hyper reliable. In addition to these 3, the IMT 2030 is planning to introduce 3 new usage scenarios. And these are the ubiquitous connectivity, the connectivity everywhere, and the integrated aspect, which is the integrated AAM communications, as well as the integrated sensing and communications. Along with these usage scenarios, the 6G also introduced new capabilities. In particular, 6 new capabilities related to the coverage, sustainability, interoperability, and interestingly, the positioning, and then sensing related and the AI related capabilities. And these capabilities will coexist with the previous 5G capabilities, such as latency, reliability, data rate, and all these systems. So the added the capabilities are supposed to provide 6G with ability to support new applications and new vertical industries, for example. So the many of these techniques, many of these capabilities, such as the high data rates and the very low latency and the positioning, many of these things can be achieved or helped by using beamforming. And the beamforming with an antenna array is related to, first of all, finding the direction, and then the pointing your signal transmission in that direction. So it is start explicitly with what you call DO estimation or the direction of arrival estimation. Without going into too much mathematics, essentially DO estimation is based on an antenna array. If you consider a linear antenna array with a certain number of elements, what you can do is that the received signal, you can represent as living in a subspace defined or spanned by what you call the antenna steering vector, or the antenna array steering vector. So by using that, that property, you can essentially estimate the angle or the direction in which the signal is arriving at the receive antenna array. There are many techniques for DO estimation, including the classic multiple signal classification algorithm, or the MUSIC, and then its variation root music as well as esprit. And there are many other algorithms that people have proposed to do the direction of arrival estimation. Now, these classic DO estimation algorithms work on the 2D plane. So we can call them estimating just a single angle on the 2D plane. And as you can see from this figure, the music, for example, or root music can do simultaneously estimating the arrival angle of multiple signals. Now, beamforming essentially allows you to transmit or receive in a particular direction. That is, if you have an antenna array, just like you can estimate the direction in which the signal is arriving at the antenna array, now you can point the transmission beam into a certain direction. Essentially what you do is that you, rather than transmitting in all directions, as in an omnidirectional antenna array or the antenna, here you will form a narrow beam of transmission energy, where the energy is concentrated in a specific spread, and then you can steer that beam in different directions as you want, so that you can point it or aim it at a particular receiver. If you are a receiver, you can actually point your antenna array to receive the signal energy from a particular direction. If you can do this, then what it does is it helps improve performance in several ways. For example, it improves the energy efficiency, because now you are not transmitting in all 360 degrees as in an omnidirectional antenna, but you are now pointing energy in a particular direction in a very narrow beam, so you don't have to increase your transmit power to maintain the same signal to noise ratio at receiver. It can also improve the spectral efficiency, because now in the same frequency or same channel, you can actually have several these narrow beams at the same time transmitted towards different receivers separated by spatial directions. So that way you can reuse the spectrum many times without interfering with each other, which also imply that you are reducing the multi-user interference. Now, this is actually also the same as when you have the sectorized antennas at the base station, and which goes back even 20, 30 years in the past. It's a common practice to use sectorized antennas where the energy is frequencies are used in different sectors of the same base station, same cell served by the base station. So you can do the beamforming both in transmit and receive directions. Also, you can point the signal in a particular direction when you are transmitting, and when you are receiving a signal, you can also tune the antenna array to receive the signal energy from a certain direction, which is essentially the same mathematical principle. Now, to do beamforming, you need an antenna array. You cannot do beamforming with a single element antenna, because then you don't have that degrees of freedom to form a beam. So here are some of the commonly used antenna models, or the antenna array models. One of them is the uniform linear array, or the ULA, where you have the antenna elements placed in a line with equal distance between each pair of elements. In the case of the two-dimensional antenna arrays, you can have plane antenna arrays, where the antenna elements are placed on a plane, either rectangular or square array, where you can have now both horizontal or and vertical direction element spacing. Or if you consider as XY direction, then the element spacing in the X direction as well as element spacing in the Y direction. They can be different or they can be the same. Another model is the uniform circular array, where you have the antenna array elements placed on a circle. And of course, there are other the 3D antenna structures as well, such as conformal arrays, where you might have antenna elements placed on cylinders and things like that. So there are many innovative antenna array designs these days that you can find. But before getting into any of those, let's get to the how the beamforming works. The simplest case to explain how beamforming works is the uniform linear array. In the case of uniform linear array, you can write the distance between two elements in the antenna array as d. Then you have the received signal at the first element. You can write as the baseband signal s of t times the e to the j 2 pi f c t, which is the carrier modulation term. Then what essentially happens is that with respect to the first element, the wavefront that reached the second element has traveled an extra distance, and that extra distance is d times sine theta, if theta is the angle that the wavefront makes with the vertical to the antenna array. So because of that, if you consider the m element in the antenna array, then you can write in general, it will have a delay of m times d sine theta divided by the speed of light compared to the first element. And this is the important point. So the received signal at the mth element, if you write, then it is going to be this baseband signal s of t delayed by md sine theta over c, and the same e to the j 2 pi f c term is also delayed by t minus md sine theta over c. Now, the classic assumption in many cases is the so-called narrowband array assumption, which means that your baseband signal is has a much narrower bandwidth compared to the carrier frequency. So which means that the s of t minus md sine theta over c you can assume as almost s of t, because compared to that small time difference, the signal has not changed much. But then the e to the j 2 pi f c t terms you can separate, so you get compared to the first element received signal, there is this additional phase factor that is e to the minus j 2 pi m d sine theta over lambda. Now, if you combine all these signal components that was received at the antenna array elements into a vector RT, you can write this as the baseband signal s of t multiplied by a theta vector, which essentially is these phase shifts, additional phase shifts experienced by the signals received at each of the antenna arrays. And this a theta we call the array steering vector. So the beamformer then is formed by essentially multiplying each of the element received signals by a weight factor, and the weights are written as the w's, and the weight vector is the w vector. So you essentially have the w Hermitian RT as the received signal, the linear combination of the antenna element received signals. So if you want to point the antenna array in a certain direction now, that is to receive the signals from a certain direction phi, for example, the west, then you can pick the w, the beamforming vector, to be the same form as the additional phase values introduced by the wavefront extra traveling distance, but instead of the angle theta, now you have the sine phi. Then the beamformer output, as you can see, simply becomes this sum over e to the j 2 pi m d over lambda sine phi minus sine theta terms, Now, as you can see, this becomes maximum if phi is equal to theta. In other words, if the antenna array is pointed towards exactly the direction where the signal is coming, the theta, then you're going to get the maximum output, which is m times the s of t. And we call the normalized beam pattern of the array as this term a phi Hermitian times the a theta and normalized by the number of antenna elements in the antenna array. So as you can see, the normalized beam pattern is maximum when the angle phi is equal to theta. In that case, you get the m times the s of t, the output signal, which means that you get an m-fold improvement in the signal to noise ratio. And in this case, because I have normalized by the number of elements, the maximum gain always stays 1. But in general, if you don't normalize, as you can see, the gain increases with the number of antenna elements. But also, when you increase the number of elements in the array, as you can see, the beam becomes narrower and narrower, which is good thing because in that case, you can have very narrow pointy beams specifically targeted towards a specific receiver or specific transmit direction. Now, this you can do in several implementations. In particular, you can do the beamforming in either analog, digital, or a combination of analog and digital. The analog beamforming you can also do either in baseband or you can do in the RF, and sometimes also in analog intermediate frequency as well. So the difference is that in the case of baseband beamforming, you're going to do the phase shifting, the waves, before doing the frequency up conversion. So you have the digital signal, you convert to analog, and then you're going to multiply by the phase shifters before you actually do the frequency up conversion to the carrier frequency. Now, the RF beamforming in the analog domain, on the other hand, you're going to first do the analog to digital to analog conversion in the case of transmission, and then that analog signal you're going to up convert and you're going to introduce the phase shifts in the RF frequency. If you're doing the digital baseband beamforming, then what you're going to do is you're going to introduce the phase shifts, those weights W's, before doing the digital to analog conversion. So you first do the beamforming in digital domain and then do the digital to analog conversion and then do the up conversion to carry frequency. Of course, as you can see, the problem with the digital baseband beamforming is that for each digital stream, you need to have a separate RF chain. So which is going to increase the complexity as well as the cost and the energy consumption of the transmitter or the receiver. So solution is to use the hybrid beamforming. So in the hybrid beamforming, what you can do is you can do digital beamforming, but then you can do the analog beamforming after doing the frequency up conversion as an additional step. So the advantage here is that you can reduce the number of RF chains you need by doing this. And the hybrid beamforming you can also do either with hybrid full array or the hybrid sub-array. In the case of hybrid sub-array, the analog beamforming you're going to not do on the full antenna array, but you're going to divide the antenna array, the total number of antenna elements you have into a set of sub-arrays, and then each individual RF chain output from the digital baseband beamforming, you're going to introduce to each of or feed into each of the sub-arrays and perform the analog beamforming. So here is a simple case of transmit and receive beamforming. In the simple case, if you consider the transmit receive beamforming problem, that you can easily characterize what is the optimal beamforming vector should be. So if you write the pre-coded transmit signal as some weighted signal of the data, the symbol D, then you can write it as S equal to WT D. The received signal you can write as Y, which is given by the rho, square root of rho, where rho is the transmit signal to noise ratio. In this case, if we assume the noise is normalized and the signal power is also D is normalized to have the unit magnitude, it's square root of rho times the H times the transmit signal S. And the H here is given by the antenna, the steering vectors at the transmitter and receiver. Where V is the transmit steering vector and the U is the receive steering vector, receive arrays steering vector. The output of the receiver beamformer, then you can write as D hat, which is given by the receive beamforming vector WR Hermitian times Y, which you can write in expanded form like that. Now the optimal beamforming problem you can write as the finding the WR, the receive beamforming weight vector, and the WT, the transmit beamform weight vector, so that you maximize the signal to noise ratio at the receiver. So by using the singular value decomposition of the matrix H, you can easily show, in this case, the optimal transmit and receive beamforming are given by the singular vectors corresponding to the largest singular value of the matrix H, the V1, and the optimal transmit beamformer is directly the transmitting in the direction of the V1 vector, which is the singular vector corresponding to the largest singular value, and the optimal receive beamforming vector is essentially a normalized version of that singular vector. The maximum signal to noise ratio in this case is essentially given by the maximum eigenvalue of the Hermitian times H matrix. Now, this is all 2D beamforming. So the 2D beamforming has been used for a long time, but the 2D beamforming has several limitations. For example, in cellular systems, it's known that more than 65% of the incident energy from a base station actually arrives at the receiver on the ground with an elevation angle greater than 10 degrees. So if you are doing the azimuth beamforming on the plane, you are going to lose much of these incident energy because they are not actually on the plane but have a larger elevation angle. And even if you go up to 40 degrees elevation, it is known that you're going to only capture about 90% of the incident energy from a base station. And also, there is another disadvantage, that is, if you use the linear arrays or one-dimensional arrays to perform the two-dimensional beamforming, with the requirement of at least the half wavelength inter-element spacing, the supporting large antenna arrays is problematic, because the larger the number of elements in the antenna array is going to be much longer because all the antenna elements are in one dimension. So even at a base station, for example, a 64 element antenna array with uniform linear array structure at 2.45 gigahertz will require about 4-meter long antenna array, which is unrealistic. But these problems, both problems of not capturing energy in the elevation dimension as well as very large antenna size that you require, you can solve by going into what we call three-dimensional beamforming in millimeter wave frequencies. Now, in the case of 3D millimeter wave beamforming, you use planar or two-dimensional antenna arrays, and this allows you to now control the beam in both azimuth and elevation directions. So as you can see, you can now separate the beams not along the azimuth direction but also the vertical direction. So you can separate the users and point the signals in both vertical direction as well as the traditional azimuth direction. But also, because you are using a planar two-dimensional antenna array, now you can actually pack more antenna elements on a smaller size real estate that you have. For example, here, as you can see, rather than using one uniform linear array for the 64 array, if you use an 8 by 8 planar array, then you're going to have only half a meter by half a meter dimension in the 2.5 gigahertz. But of course, if you go to millimeter wave frequencies, the wavelength is smaller, so the inter-element spacing that you need to avoid the grating effects in antenna combining is reduced, which means that actually you can have much larger number of antenna elements packed into a very small size antenna array. And these, for example, you can have 8 by 8 array in the millimeter wave frequencies around 30 gigahertz with about 20 millimeter by 20 millimeter plane antenna array. Now, how does the 3D beamformer works? Essentially, now you're going to combine the signals after weighting them in both horizontal and vertical directions, so X and Y direction. If you assume the antenna antenna array lies on the XY plane, as you can see, the signal you can write as the baseband signal multiplied by the antenna element radiation pattern, which is F theta phi, and some weight vector Wij. So the same principle holds now. The signals arriving at each of the elements going to travel extra distance compared to some reference point, and that extra distance is related to both the angle, vertical angle theta, as well as the azimuth angle phi. So for a signal coming from a certain direction phi theta, you can write the array factor now as the sum over both the horizontal direction, X direction, as well as Y direction elements weighted values. And if the array is pointing towards a certain direction, let's say the base station antenna array is pointing towards the phi base station and theta base station, then the weight vector, the optimal weight vector, the weight vector of the base station you can write in this form WNM, and the overall array radiation pattern is then given by that last equation in the decibel notation, which is the magnitude of the array factor AF plus the individual element radiation pattern F by theta. Now, the individual element radiation pattern, you can use different models. For example, some uses either cube of the cosine or higher powers of the cosine, like cos and theta. But simpler models in literature use the polynomials as in these equations. And with that, we come to the UAV communication, so that we now know what is the 3D beamforming and 3D beamforming in millimeter wave frequencies. The UAVs have found kind of a very broad interest in literature, both in academia as well as various applications, mainly due to the advances in the low power electronics and the miniaturization ability in recent years. And the UAVs have found many applications. And these include disaster rescue, forest fire prevention and control, and the power grid inspection, bridge inspections, as well as remote sensing, remote surveillance, aerial photography, and the more commercial applications such as package delivery. And in the agriculture, the irrigation as well as fertilizer, the fertilizing crops, and also the advanced aerial mobility, where actually you use the UAVs to transport people. And many of the emerging applications that are looked at in 6G verticals include high data rate demands. And these include augmented reality, virtual reality, and holographic or immersive communications, and many smart and connected cities, as well as intelligent transportation systems. And the UAVs also are an essential element of the space air ground 3D communication networks that are considered as part of the non-terrestrial networks in 6G. Now, with the UAV communication in various verticals, you have different type of UAV communications. For example, it could be UAV swarm communication, where you have a swarm of UAVs and there are interlinked UAV links that you are considering as UAV communication. But also in the case of UAVs integrated with the either 5G or the next generation terrestrial wireless networks, you're going to have the ground to UAV and the UAV to ground links. But in other cases, you can have a combination of these, where you have a ground to UAV, UAV to ground, but also UAV to UAV communication on the aerial link as well. And this can be the case in particular for advanced aerial mobility applications, where the UAVs, each of the UAVs need to communicate with each other so that collisions can be avoided. Now, why would we consider 3D beamforming with UAV networks? There are many uses, but two broad advantages is the spatial flexibility and the enhanced coverage. The spatial flexibility essentially goes back to the ability of the 3D beamforming to point the beams in both elevation and azimuth directions, which allows the UAV to not only serve the users that are separated on the ground plane, but also in the vertical direction, such as other UAVs, as well as even pointing the signals toward the LEO satellites. And the enhanced coverage is provided because now with the 3D beamforming, you can pack the more users into the same area and provide separate narrow beams, so you can improve the coverage, because narrow beams will propagate much further distances. Similar to the earlier 2D case, the state-of-the-art 3D beamforming in UAV networks have been proposed that uses both analog, digital, as well as hybrid beamforming. In the case of digital beamforming, similar to before the earlier case, now the antenna arrays, the plain antenna arrays, you can use to do the beamforming, apply the beamforming weights in the digital baseband and then doing the RF up conversion. The disadvantage of digital beamforming is that for each of the elements in the antenna array, now you need a RF chain separately, because each digitally weighted signal you have to upconvert separately. The similar to the 2D case, in the case analog beamforming, you will use only a one RF chain, because you're going to do the baseband. You're going to do the RF conversion first, and then you're going to do the beamforming in the analog domain. So you can hit a compromise by again using the hybrid 3D beamforming in UAV communications as well. In the hybrid, you can have again the fully connected or the partially connected case, or the full array or the sub array architectures, where in the case of the full array, you're going to use the digital beamforming, assuming that you have n RF number of antenna elements, but each n RF element is actually considered as the full array. That is, the output from each of the RF chains you're going to feed into the full antenna array N, which is going to do analog beamforming. In this case, however, the disadvantage is now you're going to have n RF times n RF parts that you need to have in your circuit, which increase the circuit complexity. The compromise again is to use the sub arrays. That is, the full antenna array, you're going to divide into n RF number of sub arrays, and then each RF chain output you're going to feed into this n divided by n RF element array to do the analog beamforming. So with this structure, now you can do various forms of 3D beamforming in UAV communications. So I'm going to review several state-of-the-art beamforming, 3D beamforming in UAV communication networks that have been recently considered considered in literature. And these are, of course, not everything, but just some representative cases. So in this, the authors have considered here joint beamforming and beam steering in the multi-UAV, multi-antenna networks. That is, you have these multiple UAVs, and each of the UAVs have multiple antenna arrays, the planar arrays. And now each of the UAVs actually going to do both beamforming and the beam steering, so that it can actually point the beams in the desired direction. The beamforming, the matrix is denoted by F, and the beam steering is denoted by H. And the goal is to find the beamforming and the beam steering matrices so that you maximize the sum rate of all the users in the network. So the problem, originally is denoted as this maximization of the sum rate over the beamforming and the beam steering matrices. And here you are considering the downlink communication from the UAVs to the ground users. This problem, as it is pretty much intractable. It's not a convex problem, because the beamforming vectors, beamforming matrices, for example, has a certain structure assumed by the assumed antenna array methodology. So the authors separate this into two separate problems, where you first do the beamforming and beam steering separately. The beamforming problem then is written as a hybrid beamforming problem, where you do both the analog and digital beamforming in the RF and the baseband. And the beam steering problem is written as the maximization of the sum rate over the matrix, beam steering matrix H. The beam steering matrix is essentially related to the angle of departure, that you try to find the best direction where you should tilt the antenna array so that actually the beam pointing error is minimized. So the authors propose two separate methods to solve these. The beamforming problem is solved by using what is called the cross entropy estimation with robustness. And the beam steering problem is formulated as a mean field game and then reduced to a Markov decision process. To solve the mean field game or the Markov decision process, then authors propose reinforcement learning-based algorithm called the mean field learning game algorithm. And it is shown that it is better than the traditional Q-learning and the algorithm or without using any reinforcement learning, both in terms of the convergence as well as the final achieved sum rate. Because the problem of beamforming and the beam steering was solved separately, to obtain the final solution, then the authors proposed to use the iterative framework where you iterate between the two solutions. That is, you first, for example, find the solution to the beamforming, assuming that you have matrix H for the beam steering, and then you'll find the beam steering matrix H, assuming that beamforming matrix F is given, and then you keep iterating until convergence. And it is shown that joint beamforming and beam steering algorithm actually performs better than the traditional methods. Another case that is considered in the literature is the hybrid 3D beamforming for UAV-aided mobile edge computing. In this case, you have a UAV-aided wireless powered mobile edge computing network with nano orthogonal multiple access or NOMA, and the both UAVs and the IoT devices in this case, which are the users, are roaming, and you have to keep tracking continuous valued angle of departures if you were to do the traditional beamforming. Instead, in this paper, the authors actually use deep reinforcement learning method called the deterministic policy gradient to achieve the hybrid beamforming, because the policy gradient approaches can track the continuous valued action spaces, in this case, the continuous valued angle of departure. And the feasible analog beamformer is then computed by using the manifold optimization. So I'm not going to go through this is the deterministic deep policy gradient algorithm adapted to this application case. So the point is that with the deterministic deep policy gradient method, you can improve the sum rate of the IoT devices in the network compared to the traditional approaches. And finally, one example is that in the case of UAV communication, how fast you need to update the weight vectors, because UAVs are moving. In this case, you consider a UAV network in which communication is between two UAVs. So UAV communication, both are moving. So you have to keep updating the weight vectors. So you can essentially formulate this problem as the maximizing the time period that you can keep your beamformer gain above a certain minimum required gain. So when the beamformer gain falls below that required minimum threshold, you want to adapt the beamformer weights. And here, depending on the mobile speed, you can see that your beamformer gain will start to fall below the required limit. And this proposed algorithm essentially learns how to keep it above a certain threshold, and just when it is needed to update, so that the beamform link between the transmitter and receiver UAVs can maintain the quality of service. So finally, some of the limitations in current 3D beamforming methods in UAV networks include the computational complexity, especially because UAVs have limited computational power and the energy resources. But computing these 3D beamformer weights, especially in dynamic scenarios, can be pretty demanding for a aerial platform like a UAV. But related to that is the sensitivity to the movement. That is, because the environment is changing, you need to adapt your beamformer weights pretty rapidly. And you also need to mitigate the interference, because beamforming can help but it can still, because UAVs are moving around in a multi-UAV network, it can be tricky to avoid each other's beams interfering with each other's transmissions. And then finally, you have the regulatory constraints that you need to also take into account, because there are the spectrum usage constraints, and also the how high these UAVs can fly and the no-fly zones, and also what transmit powers that the UAVs can use so that the transmissions are actually safe. And also there are security and privacy issues related to the UAV communications, and the handover problem can be exacerbated because the UAVs are moving around at rapid speeds. So you do need to make sure that the links don't fail, but you can maintain the links even in the presence of high dynamism. So in conclusion, UAV and millimeter wave communications are promising approaches to meet various usage scenarios envisioned in the 16xG wireless networks. But the millimeter wave frequencies, as we know, suffers from high path loss because of the high frequencies, and also certain frequencies are highly absorbed by the water and oxygen in the atmosphere. The 3D beamforming with the plain antenna array can be a good solution for these problems. Large effective aperture area you can use to obtain high gain, but also allows narrow beams focusing signal energy towards a desired receiver, reducing interference and absorption. So 3D beamforming in general, because of that, can help realize the full potential of both millimeter wave and UAV communications. All right.
So thank you for a wonderful presentation, Dr. Jayaweera. In fact, as one of the participants said, excellent session with a very detailed explanation, also supporting references that made it rather fully explainable. And I suggest anyone who wanted to know more, please write to Dr. Jayaweera directly, you will see the presentation as well as the recorded version on the website. We have a couple of questions, Sudharman. One is, what onboard sensors we need in the UAVs to be connected in the MUMA networks, and how it communicates with ground users?
What onboard sensors we need in the UAVs to be connected in the multi UAV networks, and how we communicate with the ground users. So I'm not sure exactly what you mean by these sensors here. So these are essentially the RF antennas. In that sense, if you are talking about is simply RF sensors or the RF antennas, but I'm not sure can you maybe type what you exactly mean other than that?
So Praveen, if you are here, please, please. Go ahead, Praveen. So maybe the other question, maybe we can answer. Slide 30, what is T, small t and capital T in the constraint?
Let me find slide 30, hold on. The small t is the generic time, and the capital T is the time period that you are considering, over which time period that you are performing the optimization, because things are moving, things are changing, so you need to kind of do it in time blocks and then keep updating because things are moving. So it's like a snapshot of time. This is why that certainly it will work in the dynamic scenarios, but the speed at which that you need to change things will also change. And that's actually the case that I considered in the last example, where you actually try to optimize the update time. So how fast you need to update things. So the three problems were not kind of randomly selected. So I selected the three papers so that they kind of have a thread. The last one is about optimizing how fast you need to update the beamforming weights. And certainly it will depend on the speed of movement. And this is why these are shown with this sigma naught square essentially relates to the speed of the vehicles, UAVs. And here, for example, the distance, if you consider a beam, the beam spreads. As you go further, the beam spreads. So which means that the further the distance, you can assume that the receiving UAV is going to stay within the beam much longer compared to when the distance is smaller. If you consider as something moving along the along a circle, when the radius is larger, you are traversing the same angle, but for a longer duration. So that can help. But the drawback of that is, with the distance, your energy also falls off. So there is a trade-off in that.
Yes, there is one extension to previous question that Praveen asked. He's referring to LiDAR or radar sensors.
There are both these radar or LiDAR you can use in literature. You can find especially LiDAR in this case, but also the radars. But these will relate actually. If you are not just doing the pure beamforming, but also you are trying to estimate the other UAV's movement. so that either you can track that UAV or you can track the beam and do the beam steering. So there are different ways to do it. Certainly, I mean, these days, there's a lot of work that considers that type of joint sensing and communication. So in those cases, yes, you will assume that there are radar or LiDAR on board the UAVs as well. That maybe that is what you meant by earlier question than the sensors. Yeah. And especially if you are considering the advanced aerial mobility, where you transport people using the UAVs. In those cases, you will have that type of sensors just to avoid collisions.
Wonderful. So this is a good time to wrap up. Thank you again, Dr. Sudharman Jayaweera, for an excellent session with very detailed information. I request and I suggest all the audience, please follow up on this if you have further questions to either to Dr. Jayaweera directly, or you can also reach out to me or the moderator. So thank you again and have a wonderful rest of the week. Thank you.
All right. Thank you, Kamesh. Thank you, audience. Bye-bye.